This is our kickoff event for 2024. 10 years of addressing issues, innovations, and ideas impacting and shaping our lives. Our 37th presentation. And but for the pandemic, we would have been at 41. And even during the pandemic, the speaker series partnered with the Mendel Center at Lake Michigan College in Benton Harbor, and we did some virtual events. Some of you may have attended some of those. One of them was titled The Virus and the Vaccine, and we actually had someone from the department in Washington that was dealing with all of this at that time. And so a large attendance for that one. So here we are, 10 years in. A couple years ago, we had a speaker by the name of Parag Khanna. You remember Parag? His message was Michigan was one of the 50 best places to live in the world based upon our climate, plenty of water, plenty of electricity, plenty of stable government. You don't have to worry about, somebody coming in and taking your property. He spelled out the case for it. And by the way, when he spoke, he left here and he went to Omaha, Nebraska, and he spoke to Warren Buffett's conference in May of 2021. So another one of our speakers happened to be one of the top, he was the #1 textbook author of the psychology books that high school students read. David Myers. He spoke here twice. And David wrote a book. He's written many books, but his latest one is How Do We Know Ourselves? Curiosities and Marvels of the Human Mind. The reason I mention these two books that we've talked about so far is these are people who have credentials and they're very important in the world beyond Michigan. I told my grandson who lives in North Carolina that he was a speaker here, and he said, "Was that David Myers?" And I said, "How did you know that?" He said, "Because I have his textbook." Another one was Peter Annan, The Great Lakes Water Wars. You remember that one? He's been here twice, wrote this book, became a bestseller. He has updated a couple times. He has another book out now, it's a little bit different approach, but it all has to do with fresh water and how we recycle water and the importance of recycling water. So another famous author. And this one was one of my favorites also. When Dennis Archer, former mayor of Detroit, was here and spoke, we were at Listiak Auditorium, big audience. Title of his book was Let the Future Begin. It's an amazing story about him growing up in Dowagiac, Michigan, with a father who was significantly disabled physically. Nobody had gone to college, and this guy gets a scholarship to Western Michigan. And he goes on to become mayor of Detroit, the first African-American president of the American Bar Association, and a member of the Supreme Court of Michigan. So we've got some credentials. The reason I mention all that is tonight we've got a really great speaker too that has credentials that equal everything that I've talked about so far. I have been following Drew for quite a while, and his messages are powerful. They're based on science. They're based on research and study. They're not based upon some opinion that he pulls out of the air, but they're based upon what's happening to Lake Michigan right now. And it has to do with water levels, high and low. It has to do with what's happening to the temperature of the lake as it's warming gradually now, and the impact on the fishery. It has to do with our weather. And so without any further discussion, I want to introduce from the University of Michigan, Dr. Drew Gronewold, who's going to take the stage or take the floor and be with us for the next hour or so. Welcome, Drew.
Mark, thank you so much. Thank you. I start off here with an image that I like to show in a lot of the talks that I give that puts together a lot of the issues that we're going to be talking about tonight for the Great Lakes. This is a satellite image taken from a recent winter of the Great Lakes. And what I want to point out here is the Great Lakes are an incredibly complicated system. You've heard before probably, but I'll repeat it, that they hold about 20% of all the Earth's fresh surface water. The point that I like to make when I talk about that is that there's actually 3 lake systems in the world that hold about half of all the Earth's fresh surface water. We've got the African Great Lakes, Lake Baikal, and the Great Lakes. In fact, when you put together the 10 largest lakes in the world, there's about 100 million lakes in the world. When you put together the 10 largest, including the Great Lakes, we're talking about 80% of all of the Earth's fresh, unfrozen surface water. So from my perspective, that really underscores or emphasizes the importance of understanding the Great Lakes. There's so much we can learn about how water flows into a system, how it leaves, how it's used, how it's kept clean from studying the Great Lakes. I also want to point out, if you take a look at this image, there's a lot going on here, right? There's snow on the land surface, there's evaporation happening on the lakes. There are very few scientists in the world who understand the Great Lakes to the extent that our community here in the Great Lakes does. And I think that's something that I want to emphasize throughout this talk as well. So we've already had an introduction. My name is Drew Gronewold. I'm from the University of Michigan's School for Environment and Sustainability. It's also worth mentioning that I spent some time in civil and environmental engineering and also the Department of Earth and Environment Sciences. So I'm going to go through a few different sections of this talk here. I want to give a little bit of background to the work that I do in our research group. And then I want to give an overview of some of what I'm going to call hydroclimate research. And all that means is a combination of hydrology, studying water quantity and quality, but blending that in with the climate system. So that's what I mean by hydroclimate research. And then I'm going to talk about Great Lakes water levels and how climate change is impacting water levels through a long period of history, both in the past and into the future. And then I want to mention briefly a new center we just launched. We were very fortunate just to receive about $8 million of funding through the National Science Foundation and also Canadian federal agencies to form a brand new global center for understanding climate change impacts on transboundary waters. And our initial focal point, we want to work on transboundary areas all around the world. Our initial focal point, what really sold the National Science Foundation, is that we're going to start with the Great Lakes. So we'll talk more about that, and I'll leave you with some final thoughts. So to begin, I want to mention that I don't really do a lot of work. Most of the work that you're going to see in the results and the data analysis comes from the students. So this is a picture of our student group in the backyard. We really emphasize diversity and bringing in people with a broad range of backgrounds in our research group. So most of the work that you're going to see comes from this group right here. And they're not just scientists sitting at computers. They go out and they get their hands dirty. So this is a group of a few students actually out in California in the Eastern Sierra working on a lake called Mono Lake. And I'll talk a little bit more about that later. But this is them actually uncovering some of the infrastructure to get an idea of where the water goes. And that's part of our mission as well. I also need to make sure I thank a lot of our funding agencies. Just a quick snapshot here. The big ones, NOAA, National Oceanic and Atmospheric Administration, as well as the United States Geological Survey, and many others. And in the middle here is the National Science Foundation. So without further ado, I want to walk through a quick snapshot of some of the big research projects that our group does before I dive into the Great Lakes. And the reason why is because I believe a lot of the challenges that we face in the Great Lakes regarding water abundance and water scarcity, water quality, take on a continental context, right? The problems that we're facing in the Great Lakes Basin are likely to be continental problems. And the problems that this continent faces in terms of water quantity and water quality are going to be Great Lakes problems as well. So I want to walk through a couple examples here. So this is a map of Central North America. The different colors that you see here are the big freshwater basins, the big river basins of North America. And I'm going to highlight 3 that we're going to walk through today. In the upper right-hand corner, of course, is the Great Lakes St. Lawrence River Basin. In the left-hand side is what we call the Great Basin. This is where those dry terminal lakes are, like Salt Lake and Pyramid Lake and Mono Lake. And then in the bottom there is the basin of the Rio Grande. And I'm going to talk a little bit about the work that we're doing there. I'm going to mention this again. What we're finding is that the science and the impact of climate change on water across these areas is all tied together through multinational agreements, modeling, and data. So let's take a look through first at the Western Great Basin here. And I want to just tell the context of the work that we're doing. So how many folks are familiar with the Owens River Valley? Have you guys heard about this? So this diagram is showing on the eastern side of the Sierra Nevada, Mono Lake is in the top of that red box right there, and then there's a river going down, and it's called the Owens River Valley. And there was a book written several years ago by Mark Reisner. Are you familiar with this book, Cadillac Desert? It basically talks about, in particular, some of the engineers from several decades ago, including Mulholland, who figured out a way to divert the water from the eastern Sierras as it melted down to many of the cities, including Los Angeles. So if you want to read a riveting book about the extent to which humans are willing to go to move water, check out Cadillac Desert. One of the consequences of that infrastructure is that Owens Lake is now gone. So this is a satellite image. For those who can see in the background, you can see the eastern Sierra Nevada. The valley that you see right at the base of the mountains here, that's Route 395. It's also the corridor for the Los Angeles Aqueduct. And it runs all the way down to Los Angeles, and you can see here the lake is dried out. The lake where we're doing work just upstream of that was saved in the early 1980s through some activism, and this is what Mono Lake looks like now. It's absolutely stunning. It's one of the most joyous places to do research I've ever been. And the work we're doing there is basically trying to understand how much is climate change impacting the water levels of the lake relative to the impact of the water that's being diverted for Los Angeles. And interestingly, the groups out there needed an impartial scientist to come in and do research on this because there were debates about whether or not it was climate change that was causing the lake to go down or whether it was diversions that were causing the lake to go down. And we're doing active research on this right now. Happy to talk about that more with you later on. The point is, again, that a lot of the science that we're doing on these large freshwater systems ties together across the entire continent. So next, I want to briefly just mention the work we're doing down on the Rio Grande. And this is led by one of our PhD students. Her name is Vianney Rueda. She grew up just outside of El Paso. So I'll zoom in for a bit here. Just to give you context, that red box there outlines the Rio Grande Basin. So the headwaters of the Rio Grande, up in the top of that red area, are actually quite close to the Colorado River. Can you guys all see that green area at just where that red area ends? That's the Colorado River Basin. So up in the San Juan Mountains there is where the Rio Grande originates. And one of the challenges that we face with understanding the Rio Grande is that most of the water in the Rio Grande, from the time it starts, by the time it gets to El Paso, it's pretty much gone. It's called the forgotten zone of the Rio Grande, and it's largely due to irrigation demand. So the work that we're doing, this is and by the way, I'm going to mention, I talked about my students doing a lot of work. I'm going to be showing a lot of data tonight. I hope you guys are okay with that, and I'll do my best to walk through it. But what we're seeing here is what I'm going to call a time series of flow on the Rio Grande. So on the bottom, you can see time going from 1920 up until close to present, okay? The y-axis, the vertical axis there, that's the flow in the river, and that CMS stands for cubic meters per second, which is a conventional unit of flow. By the way, keep that in mind because we're going to look at cubic meters per second of flow on the Great Lakes in just a bit. So cubic meters per second of flow on the Rio Grande, going back to 1920. The green bars, if you have one takeaway from this, let it be that the green bars represent years where flow is above average, and the reddish ones are years where flow is below average. What's the take-home message here? That Rio Grande flows have gone down dramatically. Two key points I want to make beyond that. One is, you see that gray vertical line in that graph? That's when the US-Mexico Treaty of 1944 was established. And this is absolutely critical. That treaty was established at a time when flows were high. And the agreement between the United States and Mexico said, hey, Mexico needs to keep delivering water to the United States via the Rio Grande through this treaty They can't anymore. Drought and long-term climate change have made water levels in this area so low that Mexico is consistently, I'll put in big air quotes here, violating the treaty in terms of water deliveries. What's fascinating about this is that the United States is also violating the treaty because it's supposed to be delivering water to Mexico through the Colorado River. And there's barely any water in the Colorado River that makes its way into Mexico. So again, there's another take-home message here, which is if you look near the end of this time series, do you see those green blips at the end? In a lot of the systems that we're going to talk about tonight, including the Great Lakes, there's a combination of a trend, in some cases a declining trend, whether it's ice cover or it's an increasing trend in terms of temperature, but there's also a lot of variability around that trend in a lot of these systems, and that has important, I think, implications for how we live with these systems and how we manage them. So, I want to finish off by saying that VNA and I wrote an article about this in an online publication called The Conversation. Some of you might have heard about it, but if you're interested in reading more, this is a picture that VNA took during her research. The picture that you see here, that dried out channel in the middle there, that is the Rio Grande outside of El Paso. And in fact, if you look very closely, there's barbed wire and the border wall off to the side there. So there's a lot in this story, and VNA is doing really remarkable research there. Okay, that's context. And that's some of the big picture research we're doing across the continent right now on water. Let's talk about the Great Lakes. And I want to start off by talking about a couple current events on the Great Lakes. The first is ice cover, right? So I'm guessing all of you are familiar with and concerned about and aware of the changes in ice cover that have been happening. What this plot is showing right here, even if you can't see along the bottom, so the bottom axis here are showing months from December to June. So if you guys see over here, it's showing from December to June. And this vertical axis here is ice cover in percent, going from 0 to 100. So this is Lake Michigan's historical ice cover. And every single gray line that you see here, every squiggly line is 1 year in the historical record. So you can look and you can see, okay, starting in around late December, early January, that's when ice typically starts to form on the lakes. And then it usually leaves around April or May. And you can follow that with all of those gray and blue lines. Two additional lines are on here. The red line is the average of all those years. So that represents Lake Michigan's average ice cover over time, when it starts, when it reaches its peak, and when it declines. The black line is this past winter. Some of the lowest ice cover ever in recorded history, one of the earliest departures of ice from the lake in recorded history, and we're going to talk about why. But before I do, another comment I want to mention that all the data that you're seeing here is collected by the National Oceanic and Atmospheric Administration, or NOAA, through their Great Lakes Environmental Research Laboratory. Just a tremendous resource. So I need to give credit to them, and their logo is on here. Another way to look at this data that's very common is if we look at each year and we just pick off what was the maximum ice cover on Lake Michigan. Was it 70% covered or was it 20% covered? That's what we're going to look at this next plot here. So on the horizontal axis here, we're going back to about 1972 up until present. And each of these black dots, if you look at the vertical axis here, corresponds to the maximum ice cover on Lake Michigan in every single year. So back in 1972, 73, 74, the maximum ice cover was around 30 to 40%. Okay? But there were some years where ice cover got up to 90, 95%. And what we can see is that there was a decreasing trend in ice cover over time, but it was punctuated by these years of tremendous variability, where sometimes ice cover could get close to 100%, even in the midst of this trend. So I want to let that be sort of a take-home message from this. I want to show another analysis that we did specifically on Lake Michigan. And what I'm showing here is in each one of these boxes that you see, the dots represent the total number of days of ice on Lake Michigan. The GRB, you guys know this, is Green Bay. NMI is, we've sort of broke Lake Michigan into a northern part and a southern part. So there's northern Michigan. SMI is southern Michigan. And what I want to point out here is if you look at the dots, you see how in every single panel they're kind of going down. Do you guys see that? But in a lot of news articles, they talk about a trend, a decreasing trend in ice cover. And what I want to leave you folks with is what we're seeing that's represented by those blue lines there is that the changes in ice cover and temperature, when they happen, they're happening more as an abrupt shift rather than a trend. And this is really important when it comes to our interactions with the lakes and managing the lakes. So keep that in mind. A lot of these changes are happening in shifts rather than in trends. We did this study of the entire Great Lakes for this, and we found that every single part of the Great Lakes is doing the same thing. Ice cover has definitely gone down, but it's happened in a big shift that either happened in the early 1980s for some of the lower parts of the Great Lakes, or in 1997 and 1998 for the more northern latitudes of the Great Lakes. Okay. So if any of you are interested in some bedtime reading that might put you to sleep, it's shorter than the books, so these papers might be a good read. One of them we wrote is called Fine Scale Spatial Variation in Ice Cover and Surface Temperature Trends Along the Great Lakes. And we have a lot of other papers like this that you might want to read. So here's the key question. Why? What's going on with ice cover? And I believe this figure is key to answering that question. The take home from this slide that I'm going to walk through in just a second is that winter is disappearing from Lake Michigan. And the reason we believe that is when I was working for NOAA, the National Oceanic and Atmospheric Administration at the Great Lakes Lab, a scientist decades before us had the wisdom, a scientist by the name of Nathan Hawley, some of you guys might know Nathan Hawley, he's been doing research on the Great Lakes for decades, put at the middle of Lake Michigan what's called a thermistor chain. Do any of you guys know what a thermistor chain is? Have you heard that before? Fantastic. A thermistor chain is basically a long string of thermometers separated by about 10 to 20 feet or so. But the key is that they're anchored to the bottom of the lake on a big, sometimes they use an old railway car wheel that's heavy enough. And they're suspended, but they don't quite make it to the surface. And the reason that's important is that when ice does form on the lake, it doesn't destroy the sensors. A lot of the buoys and the sensors that we put on the Great Lakes to monitor ice and temperature, they get crushed in the wintertime, so you have to take them off. This data set represents a continuous measurement of temperatures in the depths of Lake Michigan for over 30 years. Let's take a look at what we see here. So on the bottom axis, you see the month names there, January, February, March, April, May, June. Can you guys see that okay? If you can't, that's what they say. January through December. The vertical axis on the left there is depth in meters. And we've broken up the lake into this depth going from 0 down to about 100, I think it says 140 meters, okay? So in every single one of those rectangles, there is a color. And it's representing the trend in temperature at that depth and in that month across time. So for example, if you look at the very top left rectangle here that says 0, that's January's surface temperature. Okay? That's January surface temperature. And the red means that over the past 30 years, it's been warming. If you go down one box, that's the January Lake Michigan temperature at 30 meters, and then 60 meters and 75. So that's the long-term trend at each one of those depths. If you go over a little bit, that's the trend at each one of those depths in February and March and April across time. So all you have to do is just squint a little bit, and you see a big blob of red, which means so much of what we observe about Lake Michigan is at the surface, right? We see ice forming. The lake warms, the lake cools, but the real story is what's happening at the depth. And what's happening in Lake Michigan is really very similar to what's happening in our world's oceans, which is they're absorbing a tremendous amount of heat, and they can't give it off fast enough. And that's a big reason why we're seeing surface temperatures rising, but also lower ice cover and periodically more evaporation. So this was a study that we published in the journal Nature Communications a couple of years ago, and it's gotten quite a bit of attention. Okay, should we talk about water levels a little bit? Sound good? Okay, so I want to shift gears and talk about how a lot of these things tie together to lead to the fluctuations in water levels on the Great Lakes that we see. And I just want to make sure that we're all on the same page, just to make sure we all know how water is flowing through the system. So this is a map of the Great Lakes, and I'm pretty sure everyone in this room knows, but just so we're clear, up in the left-hand corner, we've got Lake Superior. Water flows out of Lake Superior through the St. Mary's River down into Lake Huron. We probably all know this, it interchanges Lake Michigan and Lake Huron, interchange in the Straits of Mackinac. They're very deep. So for the time scales we're talking about tonight, like decades, centuries, we're going to consider Lake Michigan and Lake Huron to be one big lake. I know with this crowd that's a tough pitch, but for the long term, when you take a monthly average water level, the water level is usually about the same if you take that long-term average. In any case, water then flows out through Lake Huron, down through St. Clair River, Detroit River into Lake Erie, Lake Ontario, and out. This image is going to tell the same story, but it's what we call a hydraulic profile. It's a cross-section of the lakes, showing the lakes instead in terms of elevation. So all the way on the far left, even if you can't see the words, on the far left, that's Lake Superior. And you can see where the water level is on Lake Superior. And if you go a little bit to the right, you see the water level going down a little bit through the St. Mary's River into Lake Michigan and Lake Huron. You go to the right a little bit more, that next shallow blob, that's Lake Erie. You go a little more to the right, and the water goes down over Niagara Falls into Lake Ontario and then out through the St. Lawrence Seaway. I show this because a lot of people sometimes have questions about how the water levels in the Great Lakes are connected. And it's really important to remember that water is flowing through this system, and that as Lake Superior water levels go up, they cause Lake Michigan and Huron water levels to go up. As Lake Erie water levels go down, it can increase the rate of outflow through Lake Michigan and Lake Huron. So really important connections here to keep in mind. This final plot I want to show, it's got a lot of information on it, I know. But if you can bear with me, I want to walk through the key points that are on here, okay? On the left-hand side, we've got the Great Lakes. And for each lake, can you guys see that there are 3 bars? For each lake, there are 3 bars. The bar on the left is a green bar. And that, all you got to see, even if you're in the back of the room, is how high that bar is. That green bar represents the amount of water that comes into each lake through runoff, through all the rivers and streams that come into the lakes. Okay, makes sense? The next bar, the bar just to the right of that blue bar, that's the amount of water that comes into each lake just through rainfall on the surface of the lake. Wow is right. There's really no other freshwater system on Earth where more water comes in through rain on the surface of the lake than through rivers and streams. So what that means is that the scientists that study the Great Lakes, not leaky lakes, we really have to understand how much rainfall is falling directly on the surface of the lakes. And anyone want to take a guess what that pink bar is? So we've got a green bar, a blue bar, and a pink bar. What's the pink bar? Oh, there's a lot of words there. Good guesses. Did anybody say evaporation? That's water loss through evaporation. So we have these 3 competing, I'll call them forces, coming into the lakes. Rivers and streams coming in, precipitation falling on the lakes, and evaporation. The amount of water that is coming in and leaving the lakes through these avenues is tremendous. It's like continental scale flows. You probably can't see the numbers at the top, but the number at the top of that blue bar is 2.0. That 2.0, it actually means 2,000 cubic meters per second. Okay? 2,000 cubic. Does anybody remember the flows on the Rio Grande? What were they about? About 200 cubic meters per second. So The implications here we'll get to later on, but the amount of water coming into and leaving the Great Lakes on an annual basis could completely restore the Rio Grande and probably the Colorado River as well. So just keep that in the back of your seed drive for a little bit. Okay, so that's what's on the left-hand side. On the right-hand side, somebody guessed this already. Those green bars that you see on the right-hand side of the image, even if you can't see the numbers, can you see how high those green bars are? Those represent the flows between the lakes. So the first green bar that you see is the St. Mary's River flow out of Lake Superior. Here's a take-home message for you. The last green bar that you see on the far right here, going out of Lake Ontario, the number on the top of that is a 7. That means 7,000 cubic meters per second of water are leaving the Great Lakes. By the time the flow reaches the Gulf of St. Lawrence, that flow is around 10 to 12,000 cubic meters per second. There's only one river on the entire continent that has more flow than that, and it's the Mississippi. And the Mississippi's annual average flow is around 17 to 20,000 cubic meters per second. So we already know this in this room, but I'm going to emphasize there's a lot of water in the Great Lakes, and there's a lot of water that flows from lake to lake. So this is the moment we've all been waiting for. This is a plot of long-term water levels on the Great Lakes. And this is one of the things that our lab group works very hard on. Even if we're in the back of the room here, the bottom axis that you see is time going all the way back to 1860. So there is water level data on the Great Lakes going all the way back to 1860. The vertical axis, even if you can't see the numbers, are elevations. Okay, they're water surface elevations. So the top set of blue lines that you see there, that's Lake Superior water levels over time. The next, someone said it pretty much stays the same, especially relative to Lake Michigan and Lake Huron. The next bar down are the water levels on Michigan and Huron, below that, Lake Erie, and below that, Lake Ontario. I want to spend my time talking mostly about Lake Michigan and Huron today, but we could have a beer and sit and talk about these water level variations for a long time. One of the key points I want people to notice on here is if you look at the bottom on Lake Ontario and you follow Lake Ontario through time, you'll notice that it goes up and down. By the way, the vertical range on the water level, do you guys know about how much Lake Michigan and Huron go up and down every few years? 5, 6 feet, or 1 to 2 meters. It's a tremendous amount of variability. So even though Lake Superior looks like it's not changing that much, it's actually quite a lot of coastal water level variability. If you take a look at Lake Ontario's water level variability, you'll notice right around 1960, it stops being as variable. Can you guys see that? Right around here on Lake Ontario, up, down, up, down, up, down, and then all of a sudden it's like the heartbeat diminishes a little bit. And that's because one of the key features of the Great Lakes is that the outlet is regulated by the Moses-Saunders Dam to minimize flooding. And we'll get back to that in a second here. But tonight I want to focus just on the past 20 years here on Lake Superior and Lake Michigan-Huron. And I want to start with 1997 and 1998 and bring it to the present. So if you look at that graph right there, do you see in the bottom left of the red box, Lake Michigan-Huron water levels go down dramatically? Anybody here remember that? When water levels got really, really low? Anybody remember this image? This was an image put out in the public media when water levels hit near record lows in around 2012, December 2012 or so. And basically the message here was, hey, we don't know where the water is going. It could be that people are using more. It could be that they're being put in boats. That's a call to science to come in and provide a good explanation. And so what we did is we published a paper in the journal Science called Water Loss from the Great Lakes. And here's what we showed. The bottom axis here is showing time from 1950, right around till 2015 when we published the paper. The top colors that you see there are water temperatures from 1950 till the time we published the paper. The dark blue line is Lake Michigan, Lake Huron, and the light blue is Lake Superior. And the take-home point here is that right around the time of this gray bar that you see in the middle of the image here, surface temperatures on the Great Lakes, remember I talked about jumps, not just trends? the lake surface temperatures jumped by about 2 degrees Celsius. That's extraordinary. And they stayed high. Keep that in mind for a second. The next bar down, the red bars, that shows lake evaporation. It's in millimeters. So if you see 800 millimeters of water loss, that's almost a meter, right? So you can see the red bar, one is Lake Superior, one is Lake Michigan and Lake Huron. Again, look at that jump in evaporation. And then at the very bottom, the green bars are water levels. The dark green bar is Lake Michigan and Lake Huron. The light bar is Lake Superior. And you can see that dramatic decline right around 1997. Letters A and letters B are where the lakes reached their record lows during that time period. So the take-home message is that we had an opportunity to use our science to explain why water levels were declining, and it had really important implications for management. Do any of you folks remember one of the proposals that was made during this time period about how to bring water levels back on Lake Michigan and Lake Huron? Anyone remember this?
I think I heard a talk that there's a dam up in Canada and that it's stopping the flow in Superior, and people were advocating for it to be.
So there's a bunch of typical, one is the Ogoki and Long Lake diversion of water from Canada coming in. People are talking about altering that. There was actually also a proposal that came from the 1960s to put flaps, big, large flaps in the bottom of the Detroit and St. Clair rivers to slow the flow, which would then bring Michigan and Huron water levels back up by about a foot. Those plans were put on hold in the 1960s. Why? Because water levels went up from 1960 to 1980. When water levels crashed again during this time period, those proposals came back. Well, what happened right at the same time when people were considering putting these plans in place, water levels surged again. And we wrote an article about that was in the cover of, this is a magazine called EOS. It's the outlet for a professional organization called the American Geophysical Union. If anyone you guys want to read more about this type of science, the American Geophysical Union is really the leading professional organization for this type of work. And so our article was on the cover with this iconic image of the bike path along Chicago, showing waves crashing over as water levels surged during that time period. So as scientists, we want to ask the question, when water levels go down, why did they go down? When there's less ice on the Great Lakes, why is there less ice? So let's do this one more time. When water levels went up, why did they go up? Why did water levels get so high between 2015 and now? When everyone said that climate change was going to lead to warming and more evaporation, here's why. The image on the far left shows all that precipitation falling on the lakes. Remember that? That's one of the ways water comes in. The plot in the middle shows lake evaporation over time, and the one on the right shows the sum of the two. Precipitation coming in minus evaporation leaving, okay? And even if you can't see the numbers, can you see the colors? The blue bar, the darker bars on the top are years that are above average, and the other colors are years that are below average. With me so far? All right. I've stopped the data record here at around 2013, so I can show you what happened during the time period when water levels rose. So you ready? Let's add in the data for precipitation from 2013 to present. Click. Can everyone see those blue bars? It rained like hell. For 7 years, there was an unprecedented sequence of precipitation coming into the Great Lakes, okay? Now, let's look at evaporation. So more rain is coming in. Well, if we have more evaporation, then it'll just balance out, right? Did we have more evaporation on the Great Lakes from 2014 to present? No. And the reason why is because of the polar vortex. Do you guys remember this in the news? So on the left-hand side of this image, even if you can't see the words, we see an image on the top of the Earth of a stable polar vortex and the jet stream surrounding it. But as the jet stream on the right becomes more unstable, that polar vortex, that cold mass of very, very dry, very, very cold air can wobble. And you guys remember this, right? In 2013, 2014, it wobbled right onto the Great Lakes. The lakes froze, got very, very cold, and what does that do to evaporation? So, if you have precipitation in your record highs on the Great Lakes for a few years, and you have water loss through evaporation going down, so I'll click again, evaporation went down, what happens to the total amount of water coming into the Great Lakes? It gets high. So on the far right, I'm going to click one more time, and that's the net amount of water that came into the Great Lakes. Just a tremendous amount of water leading to the flooding and the erosion problems that we all saw in the region. We wrote a paper on this, and I see some people laughing. I appreciate that. We have to sometimes be clever with our titles to get people's attention. The title of this paper, if you can't read it, is called A Tug of War on the Hydrologic Cycle of a Continental Freshwater Basin. And the tug of war, the idea here is that precipitation, rainfall coming into the Great Lakes is pulling water levels in one direction, up, right? But evaporation is pulling water levels in the other direction, down. They're in a tug of war. And the key thing is that with climate change, both of those forces on the tug of war are getting stronger at the same time. Because the atmosphere is warmer, it can hold more moisture. And that's bringing more water to the Great Lakes. Even though there was an Arctic polar vortex, the lakes are getting warmer, which means more evaporation. So who's going to win the tug of war over time? I think the key thing is that if you have a tug of war with two teams that are simultaneously getting stronger, sometimes that little knot or whatever stays in the middle, but if one team weakens up just a little bit, what happens to the middle of the rope? It swings really fast in one direction. Sound familiar? And if the other team wins for a little while or gets weakened, the water levels swing in the other direction. Folks, I believe that's what we have in store for the future. Rapid swings in water levels from one extreme to the other because precipitation and evaporation are both getting stronger with climate change. I want to finish up by just saying a couple words about this new global center. And the important thing is here, we're looking to continue talking with people. We're looking to work with communities around the Great Lakes to help solve problems related to water and climate. This is our sort of like icon image that we use to get the proposal. So it's showing something that's familiar with you guys now. It's North America. The light gray area there is all the land surface that you could consider being part of a transboundary basin. So let me say that again. The light gray that you see is part of a transboundary basin. It intersects two or more countries. Orange strip that you see along there, even if you can't read all the words, you guys see that orange strip? That's the US-Canada border. And that's where we do a lot of work through, Peter Annan mentioned this, I sit on the board, one of the boards for the International Joint Commission. And that entire domain is part of the 1909 Boundary Waters Treaty, including the Great Lakes, that we manage and we do science for. The Great Lakes is highlighted in blue because that's the focal point of our center for the next 2 to 5 years. The green, I don't know if you can squint, can you see the green polygons in there? Yeah. Those are sovereign nations, those are indigenous lands. And one of the things that we recognize in our work is that this problem of the binational cooperation between the United States and Canada really needs to be thought of as a multiple sovereign nation problem. There's a lot of voices at stake here in terms of how water comes and leaves this area. So just a couple highlights, the main themes of the work that we're doing with this global center. Here's our overall sort of Venn diagram of the different areas where we work. HC is one of our 3 areas. It stands for hydroclimate that I mentioned earlier, the blending between climate science and hydrology. And one of the things that we're trying to do is create better data sets for transboundary regions. What you see on the screen here are 2 images of precipitation across the North American continent, and I've highlighted in red areas that are wrong, where there are horrible errors in this historical data set. And the only reason we discovered those areas is because we were working on the Great Lakes. And we were trying to pull together a data set from Canada and the United States, and it turns out that there are errors in the code that are used to pull those data sets together. One of our missions of the Global Center is to ensure that there is seamless data and models on precipitation, evaporation, and runoff, so we can answer the questions we want to about the Great Lakes and elsewhere. Second main theme, ecosystems and water quality. One of our focal points, so I would love to talk with folks afterwards about what type of water quality problems you'd like to see solved in the future, and if our Global Center can help. But one area is we're partnering with the Menominee Nation to understand how the water level fluctuations that I've talked about are impacting wild rice harvests. It's just one little example of a project that we're doing. And then finally, the final node or component of our work is called community resilience and transboundary governance. So anywhere there's a community that has a need for this type of data information, we want to help address it. One of our partners on this is Six Nations of the Grand River in Canada. This is the largest collection of indigenous nations in Canada. The person you're seeing here, her name is Makasha Looking Horse. She's a 28-year-old activist. And the aquifer underneath Six Nations of the Grand River has been depleted by bottled water companies. And the challenge is that they don't have data or maps on the aquifer, the way we do on the Ogallala aquifer and other aquifers. So we're working with this group to bring them data on groundwater depletion. So where does this leave us? We are living on a continent right now where there is a growing gradient between water abundance and water scarcity. This is a fact. And this diagram is showing long-term precipitation patterns on the continent. So areas that are blue and green get a lot of water, and areas that are dark, dark red are very, very dry. Where we live, I think, on the Great Lakes, is at a hinge point between this water abundance and water scarcity. That's really important to think about. And it becomes even more important when we look at history, and just within the past few years, during those high water level periods, I don't know if you guys knew this, but downstream, during those high water years, a lot of people here were dealing with flooding and erosion. Montreal was experiencing extraordinary flooding, and that's the image that you see on the left. Thousands of homes had to be evacuated, but here's where there's some policy involved. Anybody, the image on the right to former governor, if it floods Montreal more, actually sued the International Joint Commission because they weren't able to let more water out of Lake Ontario according to this binational relationship. At the same time, upstream, communities near us are running out of water. So you all familiar with the Waukesha diversion? Yeah. So this is a diagram just to show you what the Waukesha diversion is all about. The first, Peter Annan talked about this, right? This is the first official exemption to the Great Lakes Compact, allowing water. On the right-hand side, we see the western shoreline of Lake Michigan, Milwaukee, and you can see a light blue line that shows water that is transferred from the Great Lakes Basin into Waukesha, used and then returned to the Great Lakes Basin. The first approved exemption to the Great Lakes Compact. Interestingly, does anybody know why Waukesha needed more water? Someone probably said it. There's a complex combination of claimed and actual problems going on. The original problem was radium, naturally occurring radium was contaminated in the groundwater, and they needed a clean source of fresh water. We're doing a lot of research to understand what communities around the Great Lakes Basin are going to follow suit here in terms of applying for exemptions to the Great Lakes Compact. I don't know if you guys saw this in the news a couple years ago. Anybody know the city of Joliet, outside of Chicago, ran out of water. This is an operator walking away from the groundwater pump in Joliet for the last time. Think about that. A city outside of Chicago, just outside of the Great Lakes Basin technically, ran out of water. The aquifer went dry at the same time that Lake Ontario is flooding so much that they want to let excess water out of Montreal. I don't think it takes a lot to sort of put all this together in terms of what we need to be thinking about in terms of policy. We held a forum on this in December. We got the Council of Great Lakes Governors together. We got politicians together at the University of Michigan, and we had a big discussion about the future of the Great Lakes Compact and what these discrepancies in water abundance and water scarcity are going to mean for the future of the Great Lakes.
I had a question. When the water was really, really high a few years ago, Kalamazoo ended up emptying there's a lot of inland lakes, a lot of expensive homes. Homes were getting flooded. So they emptied into what they said was just their aquifer, which everybody knows is going to end up in Lake Michigan. And they didn't file anything, and the amount was like 2,500 gallons a second. They were only supposed to do it for 2 weeks. They did it for 3.5 weeks. Not that this sounds important, but it did raise the level of Lake Michigan by 1/8 of an inch. And then, because I kept bugging them about it, and they said, oh, it's not going to Lake Michigan. And it's like, yeah, it is. So is there anything, and that was just one town that I knew of. And so when the waters get really high on these inland lakes, and the homeowners are trying to save their houses at the expense of other people's houses. So is there going to be any monitoring of that?
Your question is really a microcosm of the Lake Ontario problem, right? On Lake Ontario, they wanted to hold water or let water out so that it wasn't flooding anymore, and other people wanted Lake Ontario to hold more water in to prevent flooding downstream. I'm not as familiar specifically with Kalamazoo, but what I will say, two things. One, it's definitely an important issue, right? How are inland lakes managing excess water? Do they hold it in? Do they release it? And who suffers if they release it downstream? I'll say three things. The second thing is that I could absolutely believe that the release of water from inland lakes can cause localized flooding in some of the receiving waters. What we'd have to talk more about, though, is the extent to which a set of individual lakes, and I'm not saying this to be juxtaposition, I'm saying this to be frank, the extent to which a small body of lakes will affect Lake Michigan. So we'd have to run some numbers to find out how much that affected Lake Michigan and Lake Huron. If you look back at this plot again, remember the total amount of runoff coming into the lakes. It's a tremendous amount of runoff. But on a given year, it causes water levels in total, right? The water level fluctuations on Lake Michigan in a given year are about 12 inches for all this water. So to tease out Kalamazoo as contributing 1/8 of an inch would be tricky to do. So I'm just going to leave it and say it's an important issue, and I don't know if I can say much more on it. Yeah.
I asked Ann this, so I want to ask you.
Okay.
What keeps you up at night?
Two things. One is people from outside of the Great Lakes Basin wanting Great Lakes water, and people from outside of the Great Lakes Basin moving to the Great Lakes Basin. Now, none of those things I'm going to poke and say is necessarily a problem, but they definitely keep me up at night. And I'll punctuate that by saying the climate migration question is something that a lot of people that work on the Great Lakes are doing research on right now. And it's more nuanced than you think, right? The book Move says, hey, Michigan's a great place to move to. But here's a question. Do we have the economy to support another 10 million people? If 5 to 10 million people are here, what are they going to do for jobs, right? Maybe there's enough water and the climate's nice, but these are important questions that are one layer down. But nonetheless, climate migration and water movement keep me awake at night.
Peter Annam's book, Culture Wars, talks a lot about the compact, the 8 states and the 2 provinces.
Yep.
Not too long ago, maybe a decade or more ago, Bill Richardson from the state of New Mexico proposed that one way to solve the lack of water in western states like his was to set up a pipeline from roughly Chicago to Albuquerque, which is about the same distance as the Valdez oil pipeline. How, this is going to become a political issue in the future. That war over water, there is no more vital resource for life. Just how's that going to be enforced? If we're seeing this at a local level with cities outside the basin trying to get water, what happens when this becomes a federal issue and those states that are growing in population says, hey, that's not a resource of Michigan's, That's a resource, a national resource.
First off, the reality is if that water scarcity problems in the arid Southwest, in the Rio Grande, the Great Basin, and the Colorado River, if they really, really, really get bad enough and the states can't agree, who steps in? Deb Haaland. The Secretary of the Department of Interior steps in, and the first thing she's going to say is less irrigation for agriculture. So before plans for a pipeline or something like that really happen, they're going to irrigate less. They're going to be forced to irrigate less. So I think that's an important part of the answer to the question, that a lot of water that's put to irrigation would be diminished. A second part of the answer to that question about the politics of running a big pipeline is between the Rio Grande Basin that you see here in red and the Great Lakes, there's at least one major aquifer. There's actually several, but the one I'm thinking of is the Ogallala Aquifer. And so before people build a pipeline, they will continue drawing from the Ogallala. And it would be sort of once the Ogallala is dry and once there's no more water for all the irrigation, only then would I think the next solution be. And there's one more piece, which is desalination. And so a lot of desalination plants are being put in or proposed in the arid Southwest to solve the problem. I love your question.
As the Great Lakes warm, are we going to experience more violent weather patterns like the West Coast has?
Absolutely. Absolutely. I mean, when we talk about it in climate science, you'll hear scientists often say there's more energy in the system, right? There's more energy. Well, this idea starts with the warmer the surface of the oceans and the lakes get, the more energy, the more heat they transfer into the atmosphere, and that causes wind to be more severe. It causes the atmosphere to carry more moisture, to dump more moisture. So the answer is yes. Yep. Especially with wind speeds and storms. And I'll mention, you didn't ask this question, but especially for this crowd, increasing storm severity coupled with less coastal ice cover for protection, right? So a lot of times that coastal ice can actually help stabilize the shoreline. I know for this crowd that shoreline stabilization is a big issue. And as storms get more severe and there's less ice, that's going to exacerbate the erosion problem.
I'm curious to know what your thoughts are on the Chicago River's flow being reversed and the impact on the water levels over the last 135 years.
All right, so the question here has to do with the Chicago Sanitary Shipping Canal, and water is diverted out of Lake Michigan through the Chicago Sanitary and Ship Canal. Can you guys all see that? By the way, that was done almost a century ago to mitigate water quality problems in southern Lake Michigan. But so does anybody know about how much water flows out through the Chicago Canal? Anyone want to take a guess in cubic meters per second? Anyone want to take a guess? It's about 100 to 150 cubic meters per second, about the flow of the Rio Grande. Okay? So it's actually a lot of water. I think the calculations indicate that over the long term, that increased water, like just imagine if you have a big bathtub or a sandbox and you set up a little spigot, what's going to happen if it's a constant flow, the first thing that'll happen is water levels would go a little bit, and the calculations indicate that permanent flow out caused water levels in the bathtub to go down by about 2 to 3 inches. So water levels on Lake Michigan and Lake Huron are about 2 to 3 inches lower than they otherwise would be because of that constant outflow. I think that's the answer to your question. I know there's other questions. I'll piggyback on that by saying, I don't know if a lot of people say, well, why don't we restore 2 to 3 inches? The amount of variability that we see on the Great Lakes is much, much greater, right? 5 to 6 feet over the period of years.
I like to snowshoe. And this year I only went 6 days. I mean, I traveled in between, but what's the next 10 years going to be like for me?
Not good for snowshoeing. The proportion of precipitation, when we talk about precipitation, we talk about solid precipitation, snow or liquid. The proportion of precipitation in this region, even though total precipitation is going up, the proportion that is falling as snow is going down, and the amount of snow that does fall is staying on the ground for much less time. This actually, part of why we're studying this is, yes, we understand there are recreational benefits and all other, but this has tremendous impacts on how much runoff and when runoff enters the Great Lakes and how it affects water level cycles. We call it the dampening of the hydrologic cycle. There used to be a big spring peak, and now that's getting flattened out. So sorry to be the bearer of bad news, but that is where things are headed. Coupled with variability, I want to second this, but one of the take-home messages of tonight, right, is this idea of trends, coupled with, that doesn't mean there won't be intermittent years where all of a sudden there's a lot of snow and you can snowshoe, but the overall trend, the underlying trend is that snow is going away.
Let's thank Drew.
Thank you, guys.